Hello everyone, let us enter the wonderful world of the polar coordinate system. So, forever we have used the rectangular coordinate system that measured the distance in the x direction from the origin and the distance in the y direction from the x-axis to define a unique point P of xy. But we can also define any point in space using an angle theta in standard position and a radius r. So we fix a point O, that is our pole or origin, same origin as in the rectangular coordinates. We call them rectangular because they always form right angles between the x and the y. The grid forms boxes in rectangular systems. And so each point P in the plane can also be represented by any r and any theta. So r and theta, always in that order. Think x before y, r before theta, r theta. And we note that r is the directed distance from O to P, because if I just took any path from O to P, notice that path is much longer than the straight path, the segment connecting O to P. If I use a straight line connecting those 2 points, I get the shortest distance between O and P. And so it's important that we use that phrase directed distance. We also note that theta is measured in the same way we have all throughout our trig units. Theta is measured in the counterclockwise, that is the positive direction, formed by the polar axis and OP. And so we call that initial ray from O the polar axis. And that's just our positive x-axis where we've started all of our angles during the last 2 units. But now we know it also has a name, the polar axis. When r is negative, we will handle it a little bit differently. So remember, negative indicates direction in this system. So if you have a negative angle, it tells you open down from the polar axis rather than up. If you have a negative radius, instead of going in the direction of that angle, we're going to go in the exact opposite direction of that angle. So if we're given an angle theta and a positive r, we go along that theta towards the positive direction. But if I'm given r theta, negative r theta, then I'm going to open to that theta and then go in the exact opposite direction. So negative r theta means open to that theta and then open pi more. So we'll graph the point with the positive r and then theta plus pi. We need to go pi more to end up on that linear pair back in the opposite direction from the pole than we would usually go. So to see a nice animation of that process, you can look back at the Desmos slides if you missed that slide, but be able to graph a point or plot a point when the r is negative. So speaking of being able to plot points, let's look at a few examples. For number 1, if we have positive 2, positive 7 pi, that is my r, my radius, and this is my theta. So you can either think, let's go over 2 and then open to 7 pi over 6, which I know is a singular pi over 6 past pi. So this is the angle and this is the distance. My point lands right at 7 pi over 6. That's point A in green. You can also think open to the angle and then go the distance. Either way is fine. The order doesn't matter. But every time we're going to open and go a distance. So for number 2, we will open half a unit. So this concentric circle I've highlighted here is 1, so I'll go back 1 more circle. And 3 pi over 4 is right over here. And so our point B will be right. There's 2 pi over 3, there's pi over 4, right there. All right. Now if we're looking at number 3, we'll open to 3 and then rotate around negative pi over 3. So that means we move in the negative direction, and negative pi over 3 is coterminal with 5 pi over 3. So this is the location of point C. So I'm using this segment just for animation purposes. The point is the only piece that we are plotting, but it's helpful to think about a segment rotating with that length. For the fourth point, this is the first one where I have a negative radius, and this is when I find it helpful to think about the positive version. So if I think about the segment as just before with the positive radius of 1, and then I open to pi over 4, now I need to complete that negative version. So instead of this segment, I go back in the exact opposite direction by that radius, 1. So the point -1 positive pi over 4 actually lands right here, and I'll do it in a new color. Here is where the point D lands. Let's see, let's do another example of a negative. So in this case, we're looking for number 5, point E goes -2.5 and then 4 pi over 3. So I like to think about the positive version, open to 4 pi over 3, which is down here. And then I go back in the direction, the linear pair. So since this is the pi over 3 in quadrant 3, this point will land in the quadrant right across from that. That is the pi over 3 in quadrant 2. So here is our next point, and I'll get another color. That has a radius of 2.5 and goes back exactly another pi away from 4 pi over 3. So that is point E. Last one, and this is the trickiest kind, is when your angle is negative and your radius is negative. So here our radius is -3. I'll start with the positive version. I'll open to negative pi over 6, which is coterminal to 11 pi over 6. And then I'll go back in the exact opposite direction. So I was at the 11 pi over 6 in quadrant 4. Across from that is quadrant 2, the pi over 6 in quadrant 2. And with the radius of 3, this is where our point F lands. Some people have also talked about, instead of opening to the positive polar axis, we can go in the negative direction first and then open a negative pi over 6. So negative would be to move back in the clockwise direction by pi over 6, which also lands at point F. I find that process a little more confusing, but if that works for you, you can use it. It is only a sound process if it gets the same point every time, so check that it works with the original version. So when we name polar coordinates, we want to name all of the coterminal angles and versions of R that can land in the same place. Because I can use positive or negative radii, being able to name multiple versions of an angle is very helpful, especially when plotting a difficult angle. So while each pair of polar coordinates plots a unique point, each point does not have unique coordinates. We have infinitely many because of those beautiful coterminal angles. And so I am not going to write this formula right now because I think it is more helpful to think about this intuitively, and I don't want you to see the formula and be confused. So let's just go straight into the process of naming 3 different polar coordinates that are equal to this given point between negative pi over 2 negative 2 pi and 2 pi. This is important because we don't want to go so far away that it is not easy to locate it on the unit circle. If you go more than 2 pi, you're having to think of coterminal angles and finding where it lands on the unit circle, and that's not as helpful. So we're only going to add until it is within 2 pi, and if we're gonna add 2 pi to get a coterminal angle and it ends up greater than 2 pi, instead of that we need to go in the other direction. We will always have 2 coordinates with a positive r and 2 with a negative r. And we can represent positive and negative with positive, with that suffix VE and negative VE. So 2 positive and 2 negative r's. So we're given 1 positive. That means we're going to find 1 other positive and 2 negative r's. And I think it's really helpful to try and sketch these as we think of them. I need to turn my brightness up a little. So I need to think of a coterminal angle to pi over 3. And usually it's helpful to think of the negative coterminal angle. So 5 pi over 3 is the pi over 3 in quadrant 4. That is this angle. And so the negative coterminal angle is guaranteed to be within negative 2 pi to 2 pi. And so the negative coterminal angle there would be negative pi over 3. Now you could have done the formula, which would be to say 5 pi over 3 minus 2 pi equals, and I can think of 2 pi as 6 pi over 3 equals negative pi over 3. And since I kept r the same, I just added or subtracted a multiple of 2 pi. Now, if I'm going to think about negative r, that means I need angles that land right across in quadrant 2 at 2 pi over 3, right? Because then the negative radius will put me back on the other side in quadrant 4. So that's the first one that's easiest to come up with, is the angle that's pi away or just across from the angle when r is positive. And then again, the next angle is easier to come up with by thinking of the negative coterminal angle. So how far around in the negative direction do I have to go to get to 2 pi over 3? Well, I can find that by saying 2 pi over 3 minus 2 pi, which again we can represent with 6 pi over 3, and that is negative 4 pi over 3. So that's negative 4 pi over 3. And so that is the process I like to use to find our multiple representations of one polar coordinate. Now, if you use positive r, then theta plus or minus 2n pi. You keep the r the same. You add some multiple of 2 pi or subtract some multiple of 2 pi to the angle. Now, if you switch the sign of r, whether it was positive and you made it negative, or it was negative and you made it positive, then you need to add some odd multiple of pi. That is, add n pi. And that's functionally what happened with these 2 points, because if I have 5 pi over 3 and I subtract pi, I end up at 2 pi over 3. That is 5 pi over 3 minus 3 pi over 3 equals 2 pi over 3. So if I add or subtract an odd multiple of pi, that takes me to that angle that's right across. But I like to think about what that angle is visually because I think it's less confusing than our formulas. But you can memorize a formula if you keep r the same, multiply by an even multiple of pi. If you change r, sorry, I said multiply, I mean add an even multiple of pi to theta. If you change the sign of r, then add an odd multiple of pi to theta. Either add or subtract so that you get something in that range restriction, or sorry, theta restriction from negative 2 pi to 2 pi. I'm going to leave 8 and 9 as exercises, so please check out the posted notes for those answers to check your work. And honestly, being able to find multiple representations of these points makes them a lot easier to graph. If you know that I keep the r the same and I add or subtract 2 pi, that means negative 7 pi over 4 plus 8 pi over 4 gives me pi over 4. And so that is a little bit easier to plot, positive pi over 4, and then in the negative direction, 5 units, I get this point in quadrant 3. So there's one for you. I'll leave the rest for you. And the trickier part is finding the ones where you use +5. So I'll leave those two for you to find. So there are a couple more plotting examples and finding new names. So please use these as practice. Again, the answers will be posted. There is one here that's in degrees. Feel free to work it, but I will always be using radians as usual. Thank you for watching, and please, please, please make sure you do some homework.